Hello ladies and gentlemen, and welcome to the Quick Bit podcast, in which we teach computing quickly. Now in today's episode we will be showing you how to do 2's complement. Now 2's complement is how we represent negative numbers in binary. Now it's very easy to do. So to start with, we'll take our 8-bit binary value here. Now 2's complement only applies when there's a 1 at the front in the most significant bit. And over here we also have the least significant bit, but this is the most important currently. If this is a 0, you do not need to apply 2's complement. If it's a 1, however, you do. So, how do we apply 2's complement? Well, we start by, first of all, flipping these bits. Now, to flip the bits, what we do is we turn the 1s into 0s and the 0s into 1s. So, this value then becomes 0, 0, 0, 1, 1, 0, 1, 0. And that gives us the flipped value. Now with this flipped value, what we're going to do is we're going to add 1 to it. Now, we're going to add 1 to this flipped value. Add 1 to the least significant bit, which is here. So we're going to add 1 there. So, what does this now become? Well, if you have a look, we apply the laws of binary addition. So, a 0 and a 1 is just going to be a 1. This is going to be, and all the rest here is just going to be how they are because they're not adding anything. But if it was a 1, this would be 1 and a 1, which is 0, carry 1, and then so on and so forth. Yeah, so this value then ends up being 0, 0, 0, 1, 1, 0, 1, 1. And this is our negative representation of a number. Now, to turn this number into a binary value, it's very easy to do. To do this, all we do is just add the numbers together. So we have a 1, a 2, a 4, we have an 8 here, and we have 16. Now we can quite easily add all these numbers together. So we've got 16, 8, 2, and 1. This would be 24, 25, 26, 27. And we carry 2. And then we've got 1 and 2, which would be 37. But this would be minus 37, because we did 2's complement on it. That's the representation of 2's complement in binary. 2's complement can also be applied to floating point numbers, like this number we have here. Now, this number here is obviously represents the floating point number. Now I'm going to split this into a 10-bit mantissa and a 6-bit exponent. So we first start by splitting it here. So we have 1, 2, 3, 4, 5 and 6. Like that. Now this bit represents the exponent and this mantissa. Now here, in this bit here, is a 1. So with this bit here, it represents that it shows that this is a negative number. Whereas here, this bit here, means that it's not a negative number. If it's a 0, then it's a positive number. So what we can do is we need to flip the bits here. So that's quite easy to do. So if we just flip the bits, so we end up with a 0, 0, 0, 0, 1, 1, 0, 1, 0, 1. So the 1s have been turned into 0s, and the 0s have been turned into 1s. Like so. Now we proceed with what we did normally as well, which is to add 1 to this bit here. So, 1 and a 1 is a 0, carry a 1. Then we've got 0 and a 1, which is going to be a 1, and each one of these is going to remain the same. 1, 1, 0, 0, 0, and a 0. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We still have all the bits, which is good. Now, up here we've got the exponent. Now since it's a positive, it can just be easily converted. So we can go over here and just convert it. So we have 1, 2, 4. So the exponent is 5. So the exponent equals 5. Now what we can do is, over here, we can bring the decimal, we can write it out with the decimal point. So we're going to have 1, 2, 3, 4, 0, 1, 0, 1, 1, 0. Now we get the decimal point, and we can put the decimal point in here. Now we move it across 5, so 1, 2, 3, 4, and 5. So 1, 2, 3, 4, and 5. So the decimal point now moves here. So this means our new value is 0.0110. Now we can convert this into denary quite easily. So we've got 1 plus 2, which is going to be 3 point. So we've got this point there. And now we have a half plus a quarter plus an eighth. So we've got 0.5 plus 0.25 plus 0.125. There we go. So we've got nothing here, so it's going to be 5. Got 5, 7, 5, 6, 7, and 8. So we've got 0.875. So this value then becomes 0.875. Like so. And this value here is our 2's complement inversion of floating point numbers. Thank you for listening to the Quick Bit podcast, and we hope to see you next time. Goodbye.